What's up, everybody? Welcome to the 24th lecture of Trig. Today we're going to be talking about the last little bit that we have for the class. This is obviously the last lecture, right? So presumably it'd be the last little bit. Anyhow, so last class we left off talking about the absolute value of a complex number. And the definition said, if z is a complex number equal to a plus imaginary b, then the absolute value of z, well, that's going to be equal to the square root of a squared plus b squared. Another way we can write this is to say it's the square root of the product of a complex number and its conjugate. All right, so we're going to use this now. We've got this example here of a complex number 3 minus imaginary 5. The first thing we want to do is find the absolute value of z. And then after that, we just want to plot z. Okay. Well, using this definition here, what we've got, grab my other chalk. What we've got here is a is equal to 3 and b is equal to -5. So the absolute value of z this is going to be the square root of 3 squared plus -5 squared. So this is going to be the square root of 9 plus 25. And this, well, this is going to be the square root of 34. Okay, so let's graph this now. Well, we know that the real axis represents the real part of our complex number, and we know the y-axis represents the imaginary part of our complex number. Because of that, like we've said in past class, we're going to go over 3 units in the x-axis. So that's going to be somewhere around here. And we're going to go down 5 units in the y-axis. 1, 2, 3, 4, and 5. So that puts z right about here. Now let's take a second to look at this. If we look at this the right way, we might notice there's kind of an imaginary line going from our x-axis down to z. Well, that's going to have a length of 5, right? Yeah. -5. And from our y-axis over to z, we're going to have another imaginary line. It's going to have a length of 3. Well, we can kind of imagine moving this line up. So let's do that really quick. Well, now it looks like I have this 2 sides of a right angle triangle, doesn't it? Yeah, if I were to draw this line in right here, we'd form a triangle. Well, if that's the case, then the length of this line, well, it's going to be the square root of 3 squared plus 5 squared. So let's write that in really quick. That's a square root of 34. So this absolute value of z is equal to the distance that it's from the origin. Not just that, let's take a minute to remember what vectors did, right? Like if we had a vector like this, we could rewrite it using cosine and sine. We could rewrite it as square root of 34 times cosine of our angle, comma, sine of our angle. Now, what angle is that? Well, that would be this angle, right? Well, that must mean then that z, well, we can rewrite this z. We can rewrite it as z is equal to square root of 34 times the cosine of our angle plus imaginary I square root of 34, the sine of our angle. Now, how do I know that? How did I get there? How did I jump from this to this? Well, let's stop and think about what cosine and sine and all of this represented with vectors. The square root of 34 times cosine of theta, that represented our x value, right? The x component of our vector. Similarly, the square root of 34 times the sine of theta, that represented our y component. Well, isn't the x component just equal to our a? Isn't the y component just equal to our b? Yeah. So that must mean a is equal to the square root of 34 times the cosine of our angle, and b is equal to the square root of 34 times the sine of our angle. So that must mean then we can rewrite our complex number as the square root of 34 times the cosine of theta plus the imaginary number times the square root of 34 times the sine of theta. Let's look into this. Let's dig in a little bit. So to really quickly summarize what I was just saying. If we wanted to, we could rewrite a complex number z equal to a plus ib. We could rewrite it as z is equal to r cosine theta plus r times I sine theta. Having said that, we need to remember we have to keep all of these properties the same, right? So we can move back and forth between the two of these, however we want. We could be given a plus ib and turn it into the trigonometric form, or we can move from the trigonometric form into our traditional form, our standard form. But to do so, we have to keep these things true. Now, to help us kind of think about this, let's look at it graphically really quick. What are we saying? Well, we're saying we're given a complex number AB, or A plus IB, is what I mean to say. Well, we can think of it as sort of like a vector, sort of. They're not the same thing, and I'll explain that in a little bit. And when we do, we can rewrite, looking at it graphically, we can see that we can rewrite A as R times cosine theta and IB as I times R sine theta. Well, they both share R, so we can pull them out. We can rewrite all of this as R times the quantity cosine theta plus I sine theta. All right, now I just said that we can think of complex numbers kind of like vectors, but they're not vectors. What's going on there? What do I mean? Well, let's think about vectors for a second. Vectors were these things that we couldn't multiply or divide. Complex numbers, we can multiply and divide. So they don't have all the same properties, but they behave a lot alike. In fact, we could rewrite all of our complex numbers as two-dimensional vectors. Or we could take all of our two-dimensional vectors and rewrite them as complex numbers. So we can move back and forth between the structures, between these ideas, but they're not the exact same type of object. I just want to make that distinction here, right? So, for example, let's say we're given the complex number z is equal to 1 plus imaginary 2. Well, to plot that, that would be somewhere up here. Well, we can kind of, like I said, think about these in a similar way to complex numbers. We can imagine this as, to complex numbers. I meant to say to vectors. We can think of this similar to vectors. We can imagine this being the vector right here. In that vector, well, that vector would be one comma 2. So this tells us something else. If we think of complex numbers geometrically, we can imagine them as vectors. When we do that, we can see that if we add two complex numbers together, well, they're going to behave just like if we're adding two vectors together. So let's do that really quick. All right, so to help explain a little bit of what I mean about, we can think of complex numbers as vectors, as two-dimensional vectors, and we can think of two-dimensional vectors as complex numbers. Thought it'd help to visualize this a little bit. So what I've got here are two complex numbers, z and w. Z is equal to 3 minus 2i, and w is equal to 4 plus the imaginary number. Now, if we were to add z and w, well, that would come out to be 7 minus the imaginary number. And I went ahead and plotted them up here. So we've got z right here. We've got w right here. And we have z plus w right here. Well, for a moment, let's imagine that we have vectors from our origin to w and from our origin to z. So we've got these vectors here. First, we've got the vector u. Then, we've got the vector v. Well, looking at our graph, the vector u is equal to 3, negative 2. And the vector v, Well, it's equal to 4, 1. Now, we're going to add these two vectors together. Remember, we can think of vector addition in a graphical way, right? We can imagine moving V, the back end, the tail end of V, to the head of U. When we do that, it looks like this. Okay, well, if that's the case, I don't have any other colors. Oh. If that's the case, then the vector u plus v has to be this vector right here. So what is u plus v? What does it numerically come out to be? Well, let's look at it over here really quick. We know what u is, we know what v is. So u plus v is equal to the vector 3, negative 2, plus the vector 4, 1. Well, we know this is equal to then 7, negative 1. Wait a minute. This is the A value, this is the B value of z plus w. And this thing, well, that thing I can rewrite using sine and cosine. And in the same way you can rewrite vectors using sine and cosine, you can rewrite complex numbers using sine and cosine. And that's all we're doing here. So if you wanted to, you could turn a complex number back into a vector, find out how to write the vector in complex numbers, and then move it back over. Or you can do like what we were doing before, or you can do like what we're going to do next. Alright, so for this next example, to save us some time, I went ahead and did some of the work ahead of time. What we want to do is we want to put this complex number into trigonometric form. Well, looking at this complex number, we know that A is equal to negative 2, and we know that B is equal to negative 2 times the square root of 3. So that must mean R is equal to the square root of the quantity negative 2 squared plus negative 2 times the square root of 3, that squared. Well, if that's the case, then that means the radius comes out to be 4. Oh, okay, that's good to know, we need it. Now, next we want to find out what the angle is, right? So when we do the math, we know that tangent of theta, well, that's equal to b over a. So that's negative 2, the square root of 3, divided by negative 2. Well, that comes out to be the square root of 3. So what is that angle? Square root of 3. Well, one angle comes to mind, pi over 3, right? Yeah, because the tangent of pi over 3, that's the unit circle, and we know the unit circle tells us that the tangent of pi over 3 is the square root of 3. But if we look at where that is, that's over here. And if we look at where the graph puts us, our complex number is down here. So where are we? Like, what is this angle then? Well, tangent's pi periodic, right? Yeah. So if we add pi to this pi over 3, that's going to give us theta. So theta is going to be equal to pi over 3 plus pi. Or we can say 4 pi over 3. So what's the point of this? The point of this is to say that don't stop at just finding theta using this tangent. You're going to have to do some more digging than that sometimes. You might have to use theta, the solution to this, as a reference angle, just like what we did here. And an easy way to check that is to find out what this angle is and then compare it to where your complex number sits in the graph. Cool. Let's keep moving on. 86 that. Let's not keep moving on because I forgot the other half of this problem. We're supposed to put this in trig form, right? Okay. So, to put this in trig form, we now know that theta is equal to 4 pi over 3, and we know that our radius is equal to 4. So using what we've been talking about, that must mean z is equal to 4 times the cosine of 4 pi over 3 plus I times the sine of 4 pi over 3. 4 pi. Man, I can't write today. I times 4 times the sine of 4 pi over 3. Now we got it. Well, unfortunately, mathematicians are nothing if not sticklers about the way we write things. So we want to put this in the simplest form possible. We'll factor everything out. When we do that, we're going to get that this whole thing is equal to 4 times the cosine of 4 pi over 3 plus I times the sine of 4 pi over 3. And now that's it. Cool. So let's keep moving on. So just really quickly before we move on, I wanted to make a quick note on some vocab. When we put our complex numbers in this form, we call r the radius, we call that the modulus of z. And we call theta, the angle, we call that the argument of z. So r is called the modulus of z. Theta is called the argument of z. Cool. All right, so let's say we have two complex numbers. We've got z1, which is equal to r1 times the quantity cosine theta 1 plus I sine theta 1. Now notice these ones are subscripts, so we're only using the one to denote what belongs to what, right? Theta 1, r1, that belongs to our first complex number. Now we have our second complex number, z2, which is equal to r2 times the quantity cosine theta 2 plus I sine theta 2. Again, subscripts, they're denoting this idea of what belongs to what. Everything with ones belong together, everything with twos belong together. Having said that, if we want to multiply these two complex numbers together, z1 times z2, it's going to come out to be the product of our two moduli times all of this. So what is all of this? All of this is cosine theta 1 plus theta 2 plus I times sine of theta 1, theta 2. Theta 1 plus theta 2. And if you had looked at this and guessed that the quotient was going to be the same thing, Except subtraction, you're right, it is. Z1 divided by Z2 is equal to R1 divided by R2, that thing multiplied by all of this. So multiplied by the quantity cosine of theta 1 minus theta 2 plus I times the sine of theta 1 minus theta 2. Having said that, there is a catch here. Z2 can't be equal to 0. That's it. That's our only catch. So, let's look at an example of this really quick. Let's kind of get used to it a little bit. All right, so what we want to do in this particular example is find the product of Z1 and Z2, and then we want to find the quotient Z1 divided by Z2. All of this provided that Z1 is equal to this, and Z2 is equal to this. So how are we going to do it? Well, we're just going to apply what that last board said. We're going to say, all right, Z1 times Z2, this is going to be equal to R1, that's 2, times R2, that's 8. This all multiplied by cosine of theta 1, 2 pi over 3, plus theta 2, 11 pi over 6, plus I times the sine of the same thing, 2 pi over 3 plus 11 pi over 6. We're going to close all of that. Okay. So when we work out the rest of the math here, we'll find this is 16. This is going to come out to be 16 here. Well, 2 pi over 3 plus 11 pi over 6. We can rewrite 2 pi over 3 in terms of fractions of 6, right? So what I'm saying is we can rewrite 2 pi over 3 as 4 pi over 6. So because of that, we can rewrite this entire interior of the cosine as 4 pi over 6 plus 11 pi over 6, which is equal to 15 pi over 6. Well, we can reduce this. So what we do, we're going to get 3 pi my mistake, 5 pi over 2. Thinking about dividing by 3 and not doing the rest of the math. So we just reduced this, right? Because 15 and 6 are both divisible by 3. We get that 4 pi over 6 plus 11 pi over 6 is equal to 5 pi over 2. So we can now rewrite our cosines as cosine of 5 pi over 2. And we can rewrite our sine as the sine of 5 pi over 2. And that's it. That's all she wrote. Okay. So what about the division of the two of them? Well, when dividing the two, Z1 over Z2, the very first thing we need to check is that Z2 is not 0. Excuse me. It's not. So Because Z2 is not 0, we can go ahead and do this now. And we're going to find that this comes out to be R1 divided by R2 the cosine of 2 pi over 3 minus 11 pi over 6 plus I sine the same thing, 2 pi over 3 minus 11 pi over 6. Or we can reduce that 2 over 8. This is going to come out to be 1 over 4 times the cosine. Well, what's this 2 pi over 3 minus 11 pi over 6? I don't know. Let's find out. I'm going to write it over here. So we've got 2 pi over 3 minus 11 pi over 6. This is going to be equal to 4 pi over 6 minus 11 pi over 6, which is equal to negative 7 pi over 6. So both of these, their interiors become negative 7 pi over 6. So what we end up with then is 1 over 4 times the cosine of negative 7 pi over 6 plus I times the sine of negative 7 pi over 6. And that's it. So let's check out De Moivre's now. Alright, so we're at the end here. We're almost there. One more example after this. What I want to talk about now is De Moivre's theorem. De Moivre's theorem gives us a simple way of finding the power of a complex number. That's it. That's all it does. So let's say we've got z, and I want to raise it to a power. Let's say n. Well, let's say for right now, I gave you a complex number, a plus ib, and told you I want the 20th power of it. Without De Moivre's theorem, we have to multiply this by itself 20 times. That's going to suck. You're going to be there forever, right? What De Moivre's theorem tells us is that you don't have to go the long way. Put it into the trigonometric formula. Use the trigonometric formula. Then, if you want to raise your complex number to a power, again, let's say 20 for example, all you would have to do is raise your modulus to that power, 20. Then, take cosine of that power times your angle, 20 times our angle, plus I times the sine of that power times your angle, so again, 20 times your angle. That's going to be a lot easier to calculate than multiplying this by itself 20 times. That's going to suck. This is nice. Sucks. Nice. Sucks. Nice. And all you're doing, the worse that this gets, is putting this into trigonometric form. After that, r to the nth power, you can put that in your calculator if you wanted to. Your original angle times n, put that in your calculator if you wanted to. I expect you to do it by hand. But you could put it in your calculator. It just makes life easier. De Moivre's theorem. Love it. Know it. Get used to it. It's your new best friend. On the other hand, What if we want to go in the opposite direction here? What if we want to say, all right, I'm given a z, and I want to find what complex numbers, plural, when raised to the nth power, will give me that z back. Wait, what am I saying? What? Numbers, plural, multiple things raised to the same power can give me the same number? Yes. Yes, they can. So what we've got here is if z, a complex number, is equal to some other complex number raised to a power, all of this, right? The original number that you're given. If it's equal to r times the cosine of theta plus I sine of theta. That's what you're originally given. That's the case. And you want to find the nth root of z. Well, you're going to have n many answers. You have n many different w's here. And to find all of them, the formula we use is wk. We use k to denote which nth root we're looking at. Is it the 0th nth root, the first, the second, the third, so forth and so on. So wk is equal to the nth root of your modulus, of your original r value, that's easy enough, times the quantity cosine plus I sine, where your angles this time, well, they're going to start off with your original angle. You're going to add 2 pi k to them, and you're going to divide by n. So the nth root of some complex number z, you're going to have n many possible answers. We denote them typically using a subscript that reflects which root we're looking at. Having said that, let's see an example or two, just to kind of demystify this a little bit. All right, so hang in just a little bit longer, everyone. After this, I've got one more example, and that's it. So, to get going on this example, we're given this complex number. It's -2 plus imaginary 2. And we're asked to find all of the cubed roots of that complex number. And just for good measure, I went ahead and I graphed what our original complex number was. I claim it's going to be important in a minute. Okay, so what we know, based on what I had written on the board just a second ago, is that the solution to this question, well, it was explained to us in trigonometric form, right? That formula was in trigonometric form. So let's go ahead and write out our complex number in trigonometric form. To do that, first we need to find what r is. R is going to be equal to the square root of -2 squared plus 2 squared. That's going to be the square root of 8, isn't it? Okay. So whatever this comes out to be, we now know it's going to have the square root of 8 in it. We also know that tangent of theta, well, that's going to be equal to b over a. So let's write that out. Tangent of theta is equal to 2 over -2. Well, that's just -1. And based on where our complex number sits, we know that this angle has to be 135 degrees. So this tells us theta is equal to 135 degrees. So our original complex number we can rewrite as the square root of 8 times the cosine of 135 degrees plus I times the sine of 135 degrees and now we can apply that formula we were just talking about a minute ago. A minute ago, we had seen that if w to the n is equal to z, and z is r times cosine theta plus I sine theta, then w can be a whole bunch of values. It can be in many different answers. We can have n different w's to give us z. And all of those came out to be the nth root of r times cosine of our original angle plus 2 pi k divided by n plus I sine theta, my mistake, I sine our original angle plus 2 pi k, all divided by n. These are all the different possible values, right? Where k is equal to 0, 1, 2, etc., up to n minus 1. Okay, so using this, we're going to find out what our WKs are. Well, we know that the cubed root of the square root of 8, that's going to be the square root of 2. How do we know that? Well, we know that because 2 cubed is equal to 8. So, our WKs are going to be the square root of 2. Again, that's because we're taking the cubed root of 8, we're taking the cubed root of the square root of 8. And 2 cubed gives us 8. So, must be that our answer is going to be the square root of 2. Okay. So, now we just need to fill in the rest of this, right? So the rest of this is going to be cosine of our original angle, 135 degrees, plus 2 pi k divided by 3, plus I sine our original angle, 135 degrees, plus 2 pi k divided by 3. And k, in our case, is going to be equal to 0, 1, or 2. Now, if we were asked to give particular answers, all we would do is we'd say, all right, W1, or my mistake, W0 is equal to the square root of 2 times cosine of 135 divided by 3 plus I sine 135 divided by 3. And we do the same thing for 1, except we would put 1 in for k here, and again for 2. That's all it is. It's not as crazy as it sounds or looks. Having said that, let's look at one last example. All right, we made it. We're at the last example of the semester. And for this last example, all we want to do is solve for z. We want to solve for z in the case where z cubed minus 243, or my mistake, 343 is equal to 0. I'm going to solve this problem right here. All right. Well, looking at this, your first instinct might be to add 343 to both sides. And you would be correct. This is exactly what we want to do. We want to add 343 to both sides so that we get z cubed is equal to 343. But great, that means this just turned into an nth root problem. That sucks. I don't want to do this anymore. Too bad. We're almost done. It's actually a pretty quick problem. So, looking at this, might not be obvious how to handle this right away. After all, we got to put this into trigonometric form, right? We got to get our complex number into trigonometric form before we can apply that nth root formula. But notice, if we look at this as our complex number, right? Well, this is just 343 times cosine of 0 plus I sine of 0, right? Yeah, because it's just a real number, and it's a positive real number, so our angle has to be 0. Cool, okay. We're getting somewhere here. Now, because of this, we now know that all of our z's, our zk's, they have to be the cubed root of 343 times the cosine of our original angle plus 2 pi k divided by 3. Well, our original angle is 0, so it's just going to be 2 pi k divided by 3 plus I sine theta plus 2 pi k divided by 3 again, which again is just 2 pi k divided by 3. Okay. 2 pi k divided by 3, where k is equal to 0, 1, and 2. Well, there's a reduction here. We can reduce 343, the cubed root of it. We can reduce the cubed root of 343. Comes out to be 7. So we can make this look a little bit nicer. We can make it 7 times the cosine of 2 pi k over 3 plus I sine 2 pi k over 3, k is equal to 0, 1, and 2. And that's all it is to this problem. Having said that, I want to take and point something out here, something particularly important. Notice if we were to plot all of our answers onto a circle of radius 7, notice what happens where they lie. Our first answer is here, right? At 7, 0. Our second answer is up here at 7 over 2, comma, 7 times the square root of 3 over 2. My mistake, negative. And our final answer is right here. Negative 7 over 2, comma, negative 7 times the square root of 3 over 2. Now something cool happens here. Imagine if we were to embed this inside of a circle of radius 7. All of these are equal distant apart. If you were to measure the arc between all of these points, the arc is always the same. And this always happens. Let's say we, instead of using the cubed root, used the 4th root. We would divide our answer up, or our circle up, into 4 different parts that were evenly spaced. If it was 5 different parts that were evenly spaced. 6, 7, 8, 9, however many. That's how many points you're going to have along the boundary of your circle, and they are all going to be evenly spaced. So as a way of checking yourself, of checking your answer, graph it. See if your answers come out to be evenly spread out along a circle. Having said that, this is actually one of the more elegant parts of complex analysis, all the geometries that come out of it. But I won't bore y'all with all of that. This is just something that is important to note on. The homework does ask a couple questions about that. But with that, I'll let y'all go. Have a good break, everybody, and a good final. Have a good one.